Let me also thank the organizers for putting together this very nice workshop. Title is Symmetry Operators in Gravity, which is almost the title of the workshop if you delete the word operators. This is going to be based on two papers from a couple of months ago. In the first paper, you will recognize two names from the invitation emails we got a couple of months ago. So it's the first is in collaboration with Ibu, who disappeared, Patrick and Tom. And the second one is in collaboration with Luigi Syrian Barwatz, a student at UCLA, and Luigi Nero, a fellow postdoc at CISA. So let me start with some motivation and define the equation that we're going to analyze. So on one hand, based on arguments involving black hole physics, we expect that there are no conserved charges in a theory of gravity. And on the other hand, conserved charges are associated to global symmetries, and the modern way to look at global symmetries is in the terms of topological operators. And in fact, symmetries and topological operators in the last decade or so have become synonyms. So the question that we are going to ask in this talk is why there are not topological operators in theory of gravity. So here, let me make a few comments. I understand that in a full-fledged theory of gravity, we expect to have some kind of sum over topologies. So it wouldn't make sense to talk about a topological operator. But in this talk, we're going to take a step back, be very pedestrian, and we're going to ask whether topological operators can exist in perturbative gravity, and more precisely, we're going to consider small fluctuations around the flat background, and we're going to ask whether we can have a topological operator. So to be a bit more precise, we're going to consider a theory, a QFT, with a classically conserved current, and we're going to propose a mechanism that does not allow topological operators if we turn on gravity. So I'm going to argue, and this is going to be the main message of this talk, that even if there is a classically conserved current associated to a U1 symmetry, we still cannot define a topological operator in perturbative gravity around a flat background, and therefore we cannot have a conserved charge. So let me start with some preliminaries. A continuous symmetry is associated to a conserved current, J mu, which obeys the usual conservation equation. And typically, we exponentiate the current. We integrate along a surface, a codimension 1 surface. Here, we're focusing on. I'm focusing on a zero-form symmetry for a moment, and we exponentiate the integral and to define a topological operator. So it's as simple as here. I'm using the textbook definition of a topological operator, where I integrate J0 along a constant along the whole space. And it's a simple exercise to use Stokes' theorem and the conservation equation to prove that the derivative of u with respect to T0 is 0. So, and that's what we mean by u being topological. However, here there is already a problem. This is a composite operator. It's not well defined, and you need to provide a scheme to define it. So what we typically do is we use a Taylor series for the exponential, and we have an infinite terms, and for each term we use some point splitting procedure where we put the first in. If we have like the integral to some power, we put the first integral at time t0, the first at time t0 plus epsilon, and so on. So what in this way, we effectively spread out the topological operator in a region around T0. So in the same spirit, but in a slightly different way, we're going to use the following scheme to define this composite operator. we're going to give it a small width, and instead of integrating J0 along the surface t equals t0, we're going to integrate along the whole space with a bump function. So here you can think of the usual definition as the integral of J0 along the whole space time with a delta function that localizes the integral along t equals t0. So we're going to replace the delta function, which is a singular. Yes?
So you're saying it's composite because if you expand it, you'll have two J0s hitting each other, for example? Yeah. But if I integrate J0 just to get the Q, then the powers of Q are well-defined composite operators, no?
Well, not exactly, because we have contact terms that we need to subtract. These contact terms they show up although already at the word identity. I'm going to comment. I'm going to be a bit more explicit what the problem is.
Okay.
But the root of the problem is that we have many J0s at the same point, and we're going to regulate this defect, and we're going to replace the delta function here with the smooth function. And to be precise, we're going to consider this kind of function, which is like a smooth version of theta function, where lambda is the region where the function goes from 0 to 1. And instead of using the textbook definition, we're going to regulate this operator in this way, where in the lambda going to 0 limit, this becomes a delta function and recovers the naive definition. And I'm going to argue that although the first term makes the operator finite, it introduces some divergences in the lambda going to 0 limit. And we also need to add some counter terms to first remove the divergences, and then in correlation, and then at the end of the calculation, let's say that we are interested in calculating correlation function. At the end, we're supposed to take the lambda going to 0 limit. So here, I've chosen this regulating function, but it turns out that the result, our analysis stays the same as long as f is a smooth version of the theta function. So let me repeat again that the prescription here is that we take this operator, we insert in a correlation function, we do the calculation, everything is finite, and at the end we take the lambda going to 0 limit, which corresponds to which corresponds to the topological operator.
But what's wrong with just saying the topological operator is the thing that acts topological operator? Why do we need to define in terms of the current?
Well, because in that way you assume that you exist and you declare that it does what you want to do. Here I want to define it in terms of the fundamental fields and give a prescription that I can use to do old-fashioned perturbation theory, and everything is fine. Okay, let me.
But I don't want to not go to perturbation theory. I have a theory abstractly defined in terms of operators, and I know how the symmetry acts.
Yes.
I want
to incorporate what you're saying in the old-fashioned perturbation theory, and
but then if something goes wrong with it, I would say what has gone wrong is that you're insistent in using this language, not that there's anything wrong, fundamentally wrong with symmetries.
But in what you're saying, again, you just declare that there is some operator that does what you're what you want, right? How do you know that it exists? It actually exists.
I thought the issue, I don't know, maybe I should let you speak, but I thought the issue is to find a contradiction between this and quantum gravity.
Well, I'm not there yet. Here, there is no gravity. So far, there is no gravity. The strategy will be first to define the operator in a QFT without gravity, and see then what goes wrong if we turn on gravity.
Maybe to just further this comment, I mean, if you know how the symmetry acts, say on local operators, or as Daniel told us on the operator algebra, you can just define a topological operator by that. Say that its correlation functions are defined by its action. So I don't see any problem with that definition of the operator.
My issue with that is, how do you know that that operator exists?
I just told you. I told you how to compute correlation functions with that operator inserted.
You declare that there is an operator with certain properties. So here,
Yeah, because all I need to tell you, it's you know, if I tell you how it acts, I define it.
okay.
The question, I think, here is, can I construct the operator in terms of the fields that I use to define theory?
I guess another way to phrase the question is, if I tell you that there is a conserved current,
Wait, why does that
is there a symmetry? I guess this is the more precise question. If I have a conserved current, classical conserved current, do I have a symmetry? I guess that's what I want to answer.
But defect operators are not determined fields.
No, it doesn't.
So our point here is to argue that even if you have a conserved current, it doesn't mean that it doesn't correspond. You cannot define the topological operator if you turn gravity. I guess that's my statement. Okay.
But there's nothing wrong with the infinitesimal. Even in this, even if I accept what you're saying, this is about finite transformation. The infinitesimal transformation is still well defined.
Infinitesimal, yes and no, and let me explain why no. Okay. First of all, to even argue that this is topological in the usual way, you assume that you have an operator J mu, which there is a current which is conserved, but such thing does not exist in the quantum theory. As an operator, J mu is not conserved. So how do we even know that it's topological?
You mean because of contact terms in the Schwinger-Dyson equation?
Yeah, well, first of all, to typically prove that J mu is conserved, you use the equation of motion, but in the path integral, you're supposed to sum over all field configurations, not the ones that solve the equation of motion. So as an operator, J mu is not conserved. So
I disagree with that. So it's an issue of contact terms. It's conserved up to contact terms. Sure.
Yes, and as I'm going to argue, there are two kinds of contact terms, and the counter terms here are you need them to subtract certain bad types of counter terms. That if you let me continue, I'll show you later.
You're talking about bosonic fields, right?
Yes.
So, you're talking about the Schwinger term.
Yes.
So,
since J mu is not even conserved as an operator, how do you even show that this topological? Say operator of this kind is topological, and I'm arguing that an operator is topological if it can be deformed by a filter definition. So what do I mean by that? Assume that you insert an operator in a correlation function, and you're supposed to calculate a path integral of this type. If there is a space-time dependent field definition that I can use to deform the operator U, the position of the operator U, I would say that this is a topological operator. So in practice, what happens is because the field definition is space-time dependent, the action changes, and the change in the action with U, you can rewrite it as the operator U in a different position. So I would say that an operator is topological if I can deform it through by a field definition. And I'm going to show you in an example later on that these field definitions require to have a smooth function here and also add the counter terms to remove divergences. So let me give you an example. Let's consider a a complex scalar field. So here we have the action with the usual kinetic term and some potential, which is a function of absolute value of phi. This theory has a multiplicative U1 symmetry, and this is the associated current. And I'm claiming that the regulated topological operator that generates this U1 symmetry is this thing here, where the first term is the usual, in the lambda going to 0 limit, it gives the usual integral of J0 along space. And the second term is a counter term that blows up in the lambda going to 0 limit, and is needed to remove certain contact terms in the word identity. So in this picture, let me explain how we can recover properties of topological operators, like deforming the operator or shrinking the operator down to 0 and transform fields inside the surface of the operator. So let's in the previous example that I showed you of complex scalar, let's insert this operator in a correlation function, and I'm claiming that this operator can be absorbed by this Fourier definition. And by that I mean that if we start with this correlation function, we can do this Fourier definition and transform, remove the operator U at the cost of transforming all fields phi. And now we can take the lambda going to 0 limit, and only the function f will become a theta function, and it will transform the fields only on one side of the defect. So this Fourier definition is the analog of moving U to the right and act on the vacuum. There is we can use a similar Fourier definition which corresponds to taking U to the left and act on the Bah vacuum. And it's very similar, just put here minus sign and also change the argument of f to T0 minus T. We can also, there is also an analogous Fourier definition that just moves U slightly. In this example, it's just this Fourier definition. And this Fourier definition, I'm claiming that it corresponds to just passing U through one, in this picture, through one field. And in the lambda going to 0 limit, again, we get the expected result, where we only transform the field that we cross, and everything else stays the same.
So this is a free scalar?
This no. This is a scalar with some potential, which is a function of absolute value phi. So here, what I've argued so far is that a topological operator we need to regulate it, and a topological operator coming from a current, we need to regulate it, and it's topological because it can be moved, or it can be deformed or absorbed because with a Fourier definition. Another way.
This is if you want to insist to write in terms of the elementary fields, which
In terms of the current, yeah, in terms of the conserved current.
say is not needed.
Sure. Here again, I'm asking the question: if I give you QFT with a conserved current, does it lead to a topological operator? That's the question I'm asking. I already said this, but the kind of counterterms that we need to subtract, the kind of contact terms we need to subtract in the definition of the topological operator, they show up in word identity. So I said that as an operator, J nu is not conserved, but the conservation equations, they're actually replaced by word identities in QFT. And it turns out that if you have in the word identity with two current insertions, they're not only these kind of terms, which are the ones that you expect, but they're also contact terms coming from contractions in fields inside the J's. And these are the kind of contact terms you need to remove with the such counter terms. And although this operator doesn't look topological anymore because of the scheme we've used, it's still topological because I can deform it and do all sorts of topological manipulations using Fourier definitions. Okay, so what we have done so far is I have argued that in a topological defect you need to regulate it, and doing so we replace it with a finite tension object, which in principle the quantum theory is going to fluctuate. So in the rest of the talk we're going to view topological operators, the regulated version of topological operators, as some kind of solitonic objects, and the point will be to study the effective theory on those defects and see what goes wrong if we turn on gravity. So
could I ask? Sorry,
sure.
I've always been a little bit confused about this sort of language. From my perspective, this statement that the defect becomes a finite tension object sounds like a type error to me. The defect is a source that you define the theory in the presence of. It's not an excitation. So what do you actually mean by this?
Well, first of all, in the scheme that we use, do you agree that now we have replaced topological defect with a finite energy object?
No, I don't agree. I'd say you've replaced it with some non-topological operator, but an operator is not an object. It's a source.
Something that creates an object.
Yeah. I think it's just a language thing, but I'm not sure exactly what you mean by this.
I don't know, do you have a better...
I think the thing that you want to see is like a kinetic term.
For what?
For some mode that would correspond to it being able to move.
These would be modes of the bulk dynamical fields in the presence. Okay.
Yeah. So, which is, I think, is going to talk about something like that.
Yeah.
Okay, good.
So in the rest of the talk, the goal will be to understand what kind of fields, what kind of excitations live on these defects, and analyze the effective theory on these defects, and see how we can recover topological operator in the lambda going to zero limit without gravity, and see what goes wrong when we turn on gravity. So let's start with the universal set of coordinates that always exist. Always exist on every such object. These are the collective coordinates corresponding to space-time translations along the normal direction of the defect, and we're going to model these coordinates by promoting the position of the defect T0 into a field that depends on the coordinates parallel to the brane. And the point in the next two slides will be to understand the effective theory for this set of collective coordinates. Looking at examples, it turns out that the effective action always contains the two universal terms. The first one is a kinetic term for T0. T0 again is the models like small geometric fluctuations of the position of the brain. In principle, this is multiplied by some the tension that multiplies the kinetic term for T0 typically depends on lambda, the width of the defect, and also on the bulk field, phi. And there is a second universal term, which is the coupling of T0 with the current. And in principle, we also have higher order terms of T0, higher order interactions, which are not universal, and I'm not going to care in this talk. So the main point here is that in the absence of gravity, we can take the lambda going to zero limit, the zero width limit of these defects, and it turns out that in all in examples that the tension always blows up in the lambda going to zero limit, which means that the excitations T0, they become infinitely energetic and they freeze out. And in this way, in this limit, then we recover the topological operator that I talked at the beginning. So although we made the topological operator, we gave a scheme, and we make the operator a finite tension object, and then on top of that we assumed fluctuations. In the lambda going to zero limit, all these fluctuations, they freeze out, and we recover the topological operator. So let's now see what goes wrong if we try to repeat this analysis after we turn on gravity. And by that I mean small fluctuations are around the flat metric. So by turn on gravity, I mean we're going to write the metric as the delta mu plus kappa, which is proportional to Newton's constant, times small fluctuations. And if you repeat the analysis, again, in all examples that we looked at, there is always a universal term of this form. Here we have kappa times the tension of the defect times the trace of the metric along the parallel coordinates. So A here are the coordinates along the defect. It doesn't include the transverse coordinates. So the point here is that as we would now try to take the lambda going to zero limit, as lambda becomes smaller and smaller, gravitational interactions become stronger and stronger, and the lambda going to zero limit becomes ill-defined, and we are basically stuck with the dynamics of the collective coordinates.
Sorry, but does this already occur in perturbative gravity?
That's what we're considering here.
But then, isn't what the issue with robots using quantum has to do with non-perturbative effects?
So,
you're finding it as a violation already in one loop.
Yes. So we're trying to propose a mechanism that already does not allow to define the topological operator from a current in perturbative gravity.
But that's creepy wrong.
It's secretly non-perturbative.
It's secretly non-perturbative because if you try to take the lambda going to zero limit, then you see here that the tension blows up, and because of the gravitational coupling, the brain, it will become some kind of a black hole or something. But
because of the choices you made are very strange, right? So maybe you just made the wrong choices. Right. I feel like, I don't know. It seems like there's a more straightforward way to try to define a symmetry in perturbative quantum gravity that wouldn't have this problem.
I mean, it's just telling you that it's secretly. I mean, you're seeing that that's telling that you can't take lambda to zero, but the obstruction here is that the operator, that's the band where the operator itself wants to become a black hole.
But I don't know why I should have made the operator dynamical in the first place, for example.
Okay, that's a separate question we can discuss.
Right, so if
And
we don't do that, then I don't see where the issue comes
I think from his first part, what he's saying that if you just want to analyze this in this Lagrangian theory, so
But I can regulate, a symmetry operator in, I don't know, free field theory. You know what I have to do? Of course, there's contact singularities for the phase. I just normal order. I was not making it dynamic.
no, actually in this case we did that's exactly what we analyzed, and doing that is equivalent to giving it this width, right?
No,
And
I'm
you
just
have to
saying,
do it order by order.
2D free boson, whatever, right? All you have to do
We're not
is
doing
regulate.
we're not talking about 2D.
No,
so
it's
maybe
nothing. It's not really special about 2D though. It's just normal order.
But sorry,
Subtract the contact singularity.
that wasn't enough in the exponentiated thing where you have to do that infinite set of terms. It's the thing that was reasonable to do is to do something like point splitting, and by the time you settle, that's equivalent to giving a width to this defect. Maybe we could talk about the details.
we're just saying that the usual point splitting procedure where you split the integrals, what effectively does is it does give us a width to the defect because now because you have split all the integrals, you have separated the integrals with a small at epsilon distance. You effectively have given the defect a small width. That's what.
But sorry, but why do I have to do that? Let's do a simple. Let's take a free complex scalar in 4 dimensions.
Yeah.
So the entire dynamics of the system is captured by big theorem that tells me the only thing I need to do is that the two-point function of phi and star is 1 over x squared. That preserves the symmetry, and that's all there is. You can define a topological operator by the rule of encircling something with this three-sphere and declaring that I just capture the total charge. Now, how do I see a problem when I turn on gravity in a free complex scalar?
Well, but in what you're saying, when you're going to exponentiate the current,
I don't need to do
is
any of
already.
that. I just give you the rules. It's all about the free big theorem that respects the symmetry, and why do I need to exponentiate anything?
I don't think there's a issue with that. The question is whether the exponentiated guy I can talk about. To what degree can I talk about exponentiated guy? So that fact hasn't changed. It's just exponentiated guy that you want to know to what degree is it defined and studied.
Which generates the symmetry.
I take a three-sphere. I have a bunch of phi's and phi star. Count the number of phi's. I subtract the number of phi star. That's a total charge. That defines my symmetry operator.
The one that the operator that generates the you're talking about the infinitesimal version of the operator.
No. I just take this thing and multiply by the phase. The phase has that. I give you an operation. It's not an abstract definition. It's a vague operational definition in the case of the free scale.
So okay, what we want to do is to write down the operator. Okay, again, what we're doing is we have a current, and we ask whether you can define a topological operator from a current.
But I mean, sure, you can choose to do that. But what does that have anything to do with quantum gravity?
Because I'm saying if I give you a theory of quantum gravity with an operator which classically is conserved, to base J mu, we're claiming that how are you going to define how are you going to define the charge that is conserved?
I mean, it could be that this ultimately boils down to an insufficiency in the definition of how to relate the current to the operator. Or it could be something deeper. But I mean, I think this stands alone as a reasonable observation. There's calculations to support it. Whether or not you decide to conclude from it that it tells you something deep about quantum gravity is maybe.
And then can you repeat why this is a non-perturbative effect? Because from this slide it looks like it's just something you already see it.
What Ibu was going to say is that when you take the lambda going to zero limit and t is going to diverge, this object will feel stronger and stronger gravitational force, so you would expect to be something non-perturbative object in the theory.
In the original Gayato et al. Paper, they were working with Euclidean path integrals. So I can work with the Euclidean path integral for gravity with dimensional regularization. Okay? And the topological operator was defined by saying that I have something on a surface, and given an action, I can move that surface through things, and nothing happens unless I hit something that has some charge.
Yes.
I didn't have to say anything about operators, currents, anything.
Sure.
Okay?
Yeah.
And I can do that in the presence of a regulator that is valid in perturbation theory.
Yes.
So I shouldn't get anything that affects perturbation theory.
Again, we're going to get all what you said using a current. So again, the point is you're given you have a theory with a current, and we want to find a scheme to do this kind of manipulations that you're describing.
It sounds like you're going to get terms that violate the symmetry perturbatively in gravity.
It's almost perturbative, but again, let me repeat this point, this bullet here, that it seems perturbative. However, in the lambda going to zero limit, the brain is going to become a non-perturbative object, which we can't describe because the effective theory already breaks down here. Because the tension is going to diverge, and this is a coupling between gravity and the defect.
Yeah, but you're saying that the brain becomes black in that
Yes, yes.
And so it becomes an uncontrollable calculation. But I don't see that in this other way of looking at it.
But in the other way, you're just declaring that you have an operator that does what you expect to do. Again, right here, I'm giving a current, and I want to rederive these properties.
Can I ask a technical question that I think is related to this confusion? So how does this tension term actually appear? So what I had asked before is you had said that the operator becomes a dynamical object, and what I thought you had said was that modes of the bulk quantum fields could be proved by these gold terms. But that's not actually what you said, right? What you did is you introduced the transverse coordinate as an auxiliary dynamical field living on the operator.
Yeah.
But you can just not do that. I don't see why you had to do that. That's different from saying that it's a mode of the bulk dynamical fields, right?
It is secretly mode of the bulk because you're breaking the translation symmetry.
But you're breaking the translation symmetry explicitly by the
And the gold term associated with that is stuck on this thing. So it is secretly that. And this mode does couple to the rest of the bulk theory. You can check explicitly when you compute.
Well, I'm almost out of time, so let me give.
Yeah, maybe we should be moving this to the coffee break.
So what I said is for zero form symmetries, you can do the same analysis for one form symmetries. Blah blah blah. Same thing applies. Let me summarize. Without gravity, I claim that if you're given a current, you need to define the topological operator, you need to regulate it, but in the lambda going to zero limit, which is lambda is the width, the fluctuations freeze out, and you recover the topological operator, but in the presence of gravity, this procedure is ill-defined. So before I stop, there are two cases where you can avoid this problem. One is holography. I'm not going to talk about because already Federico already told us about it. And in this case, in this paper, they argue that when you push the brain on the boundary, the coupling to gravity renormalizes to zero, and you can avoid this problem. Blah blah blah. one more exception before I stop. You can avoid the same problem also in 2D because there is no propagating graviton. There is no there is no propagating graviton, so you can avoid this problem. And an example is the Wordsworth theory in string theory. And in this paper, we saw that if you consider toroidal compactification of string theory, there is actually an infinite number of non-invertible symmetries on the Wordsworth. Let me say a few words about these defects. We basically consider a linear sigma model that describes the compact directions of the Wordsworth. Here is a constant, phi are these compact directions. Gij is a constant metric and a constant B field. And we saw that this linear sigma model has an infinite number of topological operators which act on the holomorphic and anti-holomorphic derivatives of phi diagonally, where M and M bar are elements of OD with coefficients in Q. D is the number of compact directions. The action on d phi and d bar phi is invertible, but it turns out that the action on vertex operator is non-invertible. So this is an example of non-abelian and non-invertible symmetries on the Wordsworth. And these symmetries, they have the property that the selection rules, they depend on the topology of the space-time, of the Wordsworth, sorry, the topology of the Wordsworth. So you might say that these are broken and they have some anomaly between gravity. I would say that yes, but they still survive through dualities. Well, Jake disagrees, but I think the correct interpretation is that they are not completely broken, but they become dualities in the target space theory, exactly like axial symmetry, which is broken. It is broken, but it remains as a duality because I have the duality transformation, but now it maps correlators to a theory with a shift theta. Same thing happens here, and all these non-invertible symmetries on the Wordsworth, they lead to basically dualities in the target space theory, and the selection rules that they lead to, they are satisfied order by order in string perturbation theory. So let me summarize. I repeated the first two bullet points a few times, so let me not do it again. Let me mention a few other directions that are interesting to explore. So here, if we focus on zero-form on continuous symmetries, the question is, what about discrete symmetries? The basic problem here, we cannot repeat the analysis because there is no current. There is no current, so it's not clear how to apply the analysis, but there might be a way to do so. Another question is non-invertible symmetries. There are examples of non-invertible symmetries where we have an expression in terms of fundamental fields, like the axial symmetry, the Q mod Z axial, axial symmetry. So it will be interesting to repeat the analysis and see what goes wrong. So I have argued that, again, if you have a current, it seems that you cannot define topological operator in the presence of gravity. So now you can ask this operator, which is not this would be topological operator. The charge that this would be topological operator was going to measure whether you can put some bounds on charge violation. It will be interesting to study the RG flow on these objects, and more importantly to show that the lambda going to zero limit is a fixed point of the RG flow. And in cases where we can avoid the problem that I described, like the Wordsworth theory and string theory, it will be interesting to understand the application of the target space theory and also consider other kind of compactifications like S5 and see what we can learn using those defects. And with that, let me thank you.